So next chapter is chapter 9, rotational dynamics. What is rotational dynamics? So rotational dynamics, we study we study of forces and motions. We study of forces and motions of objects in rotational motion. We already study of forces and motions of objects in linear motion. We know how to calculate the force using Newton laws. We know how to calculate the speed, velocity, distance or displacement using kinematic equations. So when an object in rotational motion, we can study the same forces and velocities, accelerations, but it's in rotation. So therefore, in the previous chapter, you saw some equations. We use different notations. For example, like displacement in linear motion, we use x or delta x. And for rotational, we use theta. So there are some small changes, but the equations are very similar. So in this chapter, we're going to talk about forces and motions of objects in rotational motion. So the translational motion. So the figure A, you see when this person moves from here to here, his body is, all the points on his body is not moving. It moves, but inside the body, all the points intact. So he moves from one place to the another place, but every point in his body remains same. So this one is a combination of translation and rotation. Translation is going from one place to another place. So here you see the translation is going from one place to another place. In addition, he rotates around a point along a axis. So he has translational motion and also rotational motion. So it's a combination of two different types of forces. So each type we can write equations of motion and forces, and also we can combine the translation and rotation. Okay, next topic is torque. So before we go about this, let's go back to our previous lesson. We talk about Newton's second law. For example, let's assume if we have an object at rest, which means initial speed is 0. Initial is 0. And if we apply a force, it start move. So then we have a speed. So if we have a force, it is start to move. And if you have a velocity change, which means we have acceleration. Acceleration is v minus v naught over time interval. So if we have acceleration, which means we have a force, or if we have a force, on the other hand, we have acceleration, mass of the object times acceleration. So in this case, angular case, let's say we have a object which has like an axis. I can draw like a side view. This object can spin around this axis. This is the axis. It's a vertical axis. It's like a plane going through this this point into the surface, and this whole thing can spin. If we apply a force what will happen? It's going to rotate. So if we have a object which doesn't attach to anything, and if we apply a force, it has a linear motion. If the force is large enough, we can move this object to another location. If we have an object attached to like an axis, when we apply a force, it rotates. Okay, so the force and the rotation combination, we call it torque. So basically we call it twisting force. The tendency of a force to rotate an object. Of a force to rotate an object. So you can apply a force any direction. If you apply force this direction, it can rotate this way through this axis. We call it axis of rotation. So that tendency of that force, we call it torque. Okay, here's another example. It's like a door attached to the wall with a hinge right here. So we can consider as the axis of rotation. So this whole thing can turn around this point. So by experience, if we apply the force further away from this rotational point, we need a less force. If we apply a force getting closer to this axis of rotation, we need a large force to keep it straight or to rotate this. If we apply a force to an angle very close to this surface, again we know we need a large force to keep it straight or want to rotate. So depending on the location of the force and the angle we apply this force with respect to this axis, the amount of this force can change, which means the amount of torque will change. So we are going to derive a equation relating to this force and the distance from rotation axis to the force and the angle, and that relationship we call it torque. Okay, so torque, we use tau as the notation. This is the force, magnitude of the force, net force, and L is lowercase l is the lever arm. So if this is the axis of rotation and if this is the force, the lever arm L is perpendicular distance to this force from the rotational axis. Okay, so here's the rotational axis, and you apply a force, and lever arm is perpendicular direction from the force. So this is the perpendicular distance. This is the lever arm. So if you have a rotational axis here and force along this axis, so which means your lever arm is 0. So which means if you apply through the rotational axis, you cannot rotate. For example, let's say you have a disk with the axis of rotation, and if you apply a force along this rotational axis, your torque is 0 because your lever arm is 0. So If you apply a force along the rotational axis, you cannot rotate. Even if it is any arbitrary shape, it can be any shape. And if you have an axis of rotation like this, and if you apply a force through this axis of rotation, you will never be able to rotate. So this torque is zero. So in order to turn something, you have to apply a force away from this axis of rotation. Then you have lever arm. It's the perpendicular distance. This is the lever arm. Then you have a torque. Okay, so in this example, tendon exert a force of magnitude of 790 Newton. So you have a force like this, which is 790 Newton. So this is the rotational axis. So if you want to calculate the torque, which is tau, which is equal to force times lever arm. Lever arm is perpendicular distance. Perpendicular distance to the force from rotational axis, so axis of rotation. So this is the rotation axis of rotation, and the perpendicular distance is, let me use a different color. So we know this distance, and this is the perpendicular distance. So this is your L. So if you know this distance and if you know this angle, so L equals 3.6 times 10 to negative 2 sine 55. 3.2 times 10 to negative 2 sine 55. So torque is, force is 790, L is this, and you can calculate torque. So force times distance, force is in Newton, distance in meter. So unit is Newton meters. Okay, so here it shows how to calculate that. L is cosine 55 equals L over 3.6, this distance. Therefore, you can calculate L, and so torque is, this is force, this is L, 3.6 times 10 to negative 2 cosine 55. So 15 Newton meter is the unit, SI unit of torque. So equilibrium. Equilibrium. If an object is in equilibrium, whether it can be linear, it can be rotational. It true for both cases, linear motion or rotational motion. It's acceleration. Acceleration along x direction, acceleration along y direction, or rotational acceleration. This is rotational. They are zero. If an object is at equilibrium, the acceleration of the linear motion is zero, or rotational acceleration is zero. So if the acceleration is zero, means, because Newton's second law of force equals m over a, if the acceleration is zero, force is zero. So if an object in linear motion at equilibrium, means its net force along x direction is zero, y direction is zero. So similarly, if an object in rotational motion, its torque, net torque, is zero, which means it's not rotating. If an object is not rotating, which is acceleration alpha is zero, which means net torque is zero. No rotation, net torque is zero. No rotational motion. Okay, here is again a rigid body. the if a rigid body is in equilibrium, if it has zero translation or zero as acceleration, if there is no acceleration, the net force along x direction is zero, y direction is zero, or torque is zero. So we already used these two, but this is a new concept. If an object in rotational motion and if its angular acceleration is zero, which means its torque is zero. So torque is similar term for force in linear motion. So torque and force, when we talk about linear motion, we talk about force. When we talk about rotational motion, we talk about torque. Okay, I want to do a couple of examples for you to understand how this equilibrium equations, understand the equilibrium equations and how we apply these equations to solve a problem. So in the previous slide, we learned if an object at equilibrium, in equilibrium, net force along x direction is zero. Net force along y direction is zero, which means acceleration is also zero for rotational. Tau equals zero. So the net tau, net torque is zero. So we know a equation how to calculate the torque. Force times lever arm, the perpendicular distance from the rotational axis or axis of rotation to the force. So let's consider this example. A wrench is used to tighten a nut as shown in the figure. A 12 Newton force is applied. So you applying a 12 Newton force. So by experience you know this is the axis of rotation. This is the axis of rotation. So if you want to, what is the magnitude of the torque? So if you want to calculate the torque, you need force and lever arm. Force is given 12 Newton. 12 Newton. And the lever arm, so this is the force. This is the perpendicular distance to the rotational axis. Perpendicular distance, this is L, which is 7. So Newton meters. So, this is 7 centimeters. So 7 centimeters. So you have to divide by 100 to make it to meters. So then you can get answer. Okay, here's another example. String is tied to a doorknob. So this is the doorknob and string is tied to a doorknob and this length from hinge, which is the axis of rotation, this length is 0.72 meters, this length from here to here. That's not the lever arm. Okay. At an instant shown, the force applied to the string is 5 Newton. So you applying a force to the string, which is 5 Newton. What is the magnitude of the torque? Force times lever arm. So how you can find the lever arm? So you have to draw a line for the force along vertical direction. This is the direction of the force, and from axis of rotation you have to draw a perpendicular line, and which is your L. So if you know this distance using sine cosine, you can get L. L equals 0.72. You can use this angle or that angle, it doesn't matter. If you use this angle, then this is adjacent, so 0.72 cosine. or you can use, so you will get the same answer if you use cosine 33 or sine 57, because these two are equal. So you can use one of these L values to here, and F is 5 Newton, and you can calculate the tau. So when you work on uh, these problems, rotational dynamics, so you have to select the object you're going to apply, or these kinematic and Newton's laws, and then the next step is you have to draw a free body diagram and label all the forces and draw all the forces acting on the object. And then you need to use X. We normally use this as your positive X. This is your positive Y direction. And then apply net force along X direction, net force along Y direction. And if there is a rotational force, then you have to draw the torque. Then apply equations that specifically balance the forces. If it is equilibrium, then you have to use net force along X direction is 0, net force along Y direction is 0, and net torque is 0. And then select a convenient axis of rotation if it is a rotation. So in the next example, I will show you what this means, convenient axis of rotation, and then solve the equations. So in this particular example, you have like a knife edge, very sharp edge, and it's like a board, and here you have attached to a bolt, and then you have a sharp edge sitting on this board on a sharp edge. So now the question is axis. Okay, so as in the instructions on the previous page, you can select this point as an axis of rotation, or you can select this point as an axis of rotation, because at the end your net torque is 0. So if you consider this point as axis of rotation, we know if you have a person, we have a weight of that person pointing downward. So if you choose this as axis of rotation, then you have a force from the bolt on this board pointing down, and you have a force here. So this force becomes, the torque from this force becomes 0, because your L, the lever arm is 0, but you have a distance from this point to this, and you have to use that as lever arm for this weight, and then you have to consider this length for torque from this bolt, the force acting on the board from the bolt. So you have two forces contribute to the torque. So if you use this as axis of rotation, you don't have to consider this force, because your lever arm is 0, because it is right on the axis of rotation. But then you have to consider this force. This is the lever arm 2, which is 1.4, and then for the weight force you have another one, 3.9 meters. So each force you have a lever arm. So when you calculate the net torque, if it is equilibrium, it is 0, which is equal to F2 times L2. L2 is 1.4, and then plus or minus, I will tell you what you're going to use, W times the length, 3.9. So okay, so in the previous example I put plus or minus here. So which sign you're going to use? So let's consider net torque is 0. That's the equation we learned. If an object at equilibrium, net torque is 0. So there are two forces acting on this, F2 and W. Okay, so if this is the axis, okay, this is your plus X direction, this is your plus Y direction, this is your plus torque if the object is rotating this direction. So because of this force, we can see this thing rotates that way. Therefore, it's a plus 1. So F2 times This is the lever arm. The perpendicular force from the axis of rotation to this force, which is 1.4. So net torque is F2 times 1.4, and let me use a different color. So now you consider the W, which is pointing down, and the lever arm, this length, is the perpendicular distance to W from the rotational axis, which is 3.9. And because of this, it tends this way, which is a negative, because we consider counterclockwise is a positive, therefore clockwise is negative. So that's why you have a negative. So you have to have a negative W times 3.9, so which is equal to 0. So if you solve F2 times 1.4 negative W, we know that, and then 3.9, so 530 is W times 3.9, which is equal to 0, and then you can solve for F2, which is 1480 newtons. So now you have calculate F2, which is 1480, W equals 530, and only thing we don't need in this, we don't know in this problem, is F1. So if you use, if it is in equilibrium, net force along y direction is 0. So this is plus, because it's in positive y direction, 1480, and F1 is a negative one, and negative W2, which is 530, which is 0. So now you can solve for F1, which is equal to 1480 minus 530. And then you can use this linear equation to calculate the remaining force. So whether you use this as rotational axis or whether you use this as rotational axis, you still get the same forces once you calculate these forces. Okay, here's another example. The arm is horizontal and weigh 31 newtons. So this is your arm and this is your shoulder joint. This is basically the axis of rotation. Okay, so this deltoid muscle is applying a force to keep the arm in horizontal position. So because of this force, which is given 1840 Newton. So 1840 force is providing the support to keep the arm along a horizontal plane or horizontal line. So in addition to the weight of the arm, so arm has a weight because of the gravity, we know it's pointing down, so 31 Newton. In addition, if you hold in a dumbbell on your hand, you know, it creates another force, weight force of the dumbbell, WD. So it's also pointing down. So these two forces, weight of the arm and the weight of the dumbbell, both are pointing down, which means it gives a negative torque, which means it's negative value. And because of this force applied from the muscle, you can keep this balance so in equilibrium. So because of this force, this arm can rotate clockwise. Therefore, it's a positive torque. This torque is balanced. This negative torque contribute from the weight, and also another negative torque contribute from the dumbbell. So we have three torques. Two of them are negative. Torque from the dumbbell, torque from the hand, weight of the hand, and then torque from the muscle. So there are three forces. They are at equilibrium. Therefore, net torque is 0 because it's at equilibrium. So two of them are negative, two of them are positive. I will show you how to write the equation force times lever arm. the perpendicular distance from the axis of the rotation to each force in the next slide. Okay, here the axis of rotation, axis. So if you consider the rotational axis, consider this force M, and let me use a different color. So M is the force, and the perpendicular distance is this. So if you know this distance, which is 0.15 meters, this angle is 13 degrees, so this is opposite, therefore it's a sine. So torque is equal to 0, which is force from the muscle, and the distance lever arm is 0.15 sine 13, which is a positive force because it's the torque from the muscle is counterclockwise. This is a positive torque, and then you have a negative torque from the weight of the hand, which is given, and the length or lever arm, which is the axis of rotation to the perpendicular distance, which is 0.28. So weight of the hand times the distance, 0.28, minus, because this force contribute a negative torque because because of this force, because of this weight force, the whole thing, hand try to rotate clockwise direction. So therefore you have a negative one, and also similarly because of the weight of the dumbbell, it also creates a negative torque. So which is equal to W dumbbell times the lever, the perpendicular distance to this force, which is 0.62. So weight of the dumbbell times 0.62. If you add these three forces, since it's equilibrium, they equal to 0. So weight is given, therefore you can calculate the weight of the dumbbell. Weight of the hand is given, weight of the force given from the muscle is given, so you can calculate the weight of the dumbbell. So when you substitute WA, weight of the hand, force from the muscle, you can get the weight of the dumbbell, which is 86 newtons. Next topic is center of gravity. So center of gravity of a rigid object is the point at which its weight can be considered at when the torque due to weight is being calculated from. Okay, let me give you an example. Let's consider a meter stick. So 1 meter, which is 100 centimeters. Let's say its weight is 100 newton. So if you split this into 100 units, so which is 100 centimeters, 1 centimeter, each centimeter contribute 10, each centimeter contribute 1 newton. So each centimeter is 1 newton. So 100 centimeters, each 1 newton, so contribute to, but because of the uniformity, we can consider the right center because of these weights, because it's symmetric, because of the symmetricity. You know, if you have one weight here and if you get another centimeter here, so each contribute 1 newton. So if you consider the symmetry, we can consider the total 100 newtons is concentrated at the center of this stick. So therefore, when you get a weight force, we mark at the center, which means from one corner it's just 50 centimeters. So it's easy for us to do calculation. So let's say if a meter stick attached to a hinge, so we know it has a weight when you label the weight, we just use the center, and this length is half of the length of the meter stick, which is like 50 centimeters. And if you have an irregular shape, then it's very hard for us to tell. So then we have to have a formula to figure out where the weight, or that point we call it center of gravity. Okay, we have a formula to calculate the center of gravity. Position of the center of gravity, which is equal to, if you have an irregular shape, if you split into W1, W2, and if this is the center of gravity, this is X1, this is X2. So this object can split into small sections, masses, and we can measure the length. And using this equation, we can get the center of gravity of this object. In this example, you asked to calculate the center of gravity of the arm relative to the shoulder joint. So with respect to this point, what is the X center of gravity? So upper arm has a weight, and you can use the center of the upper arm, which is 0.13 times 0.13 times weight 1, and this length times this weight, which is 0.61 times weight of lower arm. And then hand, again you can take the center of the hand with respect to this point. So X center of gravity, you can, in the next slide I will show you the, okay, here's weight of the upper arm, W1, X1, distance from the shoulder joint to the center of gravity of the upper arm. Lower arm weight, W2, X2, distance from center of gravity from the lower arm to the shoulder joint. And the hand, center of gravity of the hand, and distance to the shoulder arm, X3, and W3, and W1, W2, W3. So basically we split the arm into 3 sections. Here, here, here. Each has a weight, and with respect to the, so if you consider one arm as a one unit, the center of gravity is 0.28. So it's somewhere around your elbow. This is 0.28 from shoulder joint. So this is the weight of the entire arm, 0.28 from your shoulder joint. That's the center of gravity. Okay, Newton's second law we're going to apply to rotational motion. So we, in previous chapters, we talk about Newton's second law, which is for linear objects, net force acting on an object, which is equals to mass times acceleration of that object. So in this case, this person is holding a string. Other end is attached to an airplane, and which is on this rotational path, and this length is the radius, which is perpendicular to this force. So the force, tangential force, is equal to, so we just apply Newton's law to this case. So here the force is tangential force, because it is tangent to this axis circle, and mass of the airplane times acceleration also in this direction of the force, tangential acceleration AT. Okay, so MAT. So same equation. So but we learned that tau, the torque, is equal to force times lever arm. We just talk about this. So if you apply a torque for this case, which is equal to force times lever arm. Lever arm is the perpendicular distance to this tangential force R. So instead of Ft, I can write torque tangential force times R. And then I can solve for tangential force Ft, which is equal to tau over R. Instead of Ft, I can write tau over R, m. Acceleration also we can write in terms of radius times rotational velocity R alpha. So now you have tau over R, which is equal to mR alpha. So if I rearrange this equation a little bit, tau equals m r square, this r multiplied with this r, times alpha. So in this equation, tau, which is equal to mr square times alpha. The reason we write mr square in parentheses because we want to compare this with Newton's second law, ma. So linear case acceleration, linear acceleration is proportional to linear force. And rotational case, instead of linear force, we talk about torque, which is proportional to angular acceleration. So instead of mass, we have mr square. So this mr square, we call it moment of inertia. For rotational, instead of force, we talk about torque, acceleration, rotational acceleration. Mass, we call it moment of inertia. Okay, so net torque equals mr square times alpha. So if you consider a rigid object, so this object can split into small sections, just like when we find a equation for center of mass, which is individual weight times position, or the distance to a given point, x2, etc., divided by W1, W2. So similarly, we can write net torque contribute from each section times the acceleration of each section, tau 1, tau 2, up to tau n. We can split this object into n, and we can use this equation. Net torque equals net moment of inertia from all these small sections contribute to the net torque times angular velocity or angular acceleration. Okay, so net torque equals I alpha. I is moment of inertia, which is mr square alpha. So I is moment of inertia.